All right, hey everyone, it's Active InferAnt stream number 007.1, and it should be a great and exciting stream. It's November 7th, 2024, 7/11, depending on where you are. And I'm going to begin the stream with a GitHub push that we are going to spend the next several hours probably unpacking. Let's commit it, push it, and begin what will be a very fun exploration into the Active Inference Institute's branch of PyMDP. While it's writing, let's jump into the show. Here's where we're heading. We're heading into Shapley value analyzed homeostatic satisfaction, expected free energy, belief accuracy, and control efficiency analyses for multiple differently parameterized PyMDP agents, base, risk-averse, exploratory, and balanced on those measures. Being able to analyze combinatorics like the synergies of their belief accuracy, control efficiency, expected free energy, and homeostatic satisfaction. We can look at the report and explore different topics like, with respect to those variables, what's the mean Shapley contribution, coalition performance, best coalitions. This is all combinations of 0, 1, 2, 3, and 4. So for example, for expected free energy, we see that the 4-unit coalition is the best. Whereas for homeostatic satisficing, agent 0 working alone does the best. Underneath these coalitions and their combinatorics are specific agents that are logged in individual experiments. And here's some of the plots and how that looks for each individual agent. This is a given active inference agent. Here we have policy entropy over time, action selection distribution, belief observation cycle, belief accuracies over time, homeostatic state distributions and trajectories, state transitions, policy selection probability, policy updating, decrease, maintain, and increase, belief dynamics through time, hidden state beliefs, action frequencies, policy convergences, belief convergences, correlations between beliefs and actions, and action confidences. So what that Shapley analysis is doing is running all the combinatorics under the hood. This is going to be a wild ride. So let's confirm that the GitHub has pushed. I'll put the code link in. Welcome to the 007 fork. In the live chat, I will look forward to everyone's comments. I am going to ensure that we are pushing the right way. It still has not loaded. Let's begin, though, with the 007 here. Taking a little bit of time to upload on GitHub. Okay, here we go. A little bit more context before we dive into what may be some absurdly technical, but really useful and interesting things that have happened over the last few days and hours. Here's the stream. GNN for AgentMaker, for PyMDP, for Active Inference Biofirms, for Bioregionalism, for ants? Let's decompress that title. Generalized notation, GNN, as semantic middleware for AgentMaker, a custom robust modular agent engineering framework using PyMDP, Python language package for Markov decision processes with methods for active inference and free energy-based inference methods for biofirms, as proposed by John Clippinger as a paradigm for firms in the age of bioregionalism as a mode of life, coexistentialism for species like ants, people, and beyond. Here's some live stream code names and an only lightly redacted preludium for your priors only. Predictions are not enough. The agent who minimized me. On Her Majesty's Statistical Service. Quantum of Precision. Live and let update. Professor Friston, do you expect me to reach the optima? No, I expect you to optimize. just like they wrote at the end of the 2022 textbook, when the last words were, ultimately, we are confident that you will continue to pursue active inference in some form. Is that agent's generative model an MDP? Yes, an MDP, a PO MDP. As if the media were not already the message for you. This is a just-in-time live stream going through raw open source code. I know that there are bugs, as well as typos, incorrect or ineffective calculations, other errors. This is speculative realism embodied in chaotic large-scale code coordination using Cursor 0.42.4 and Claude 3.5 Sonnet 2024-1022. Use these linguistic and computational symbols at your own risk and delight. If and as you are so inclined, you are invited to join our adventure and journey, partially disclosed herein now. Let's check again in the GitHub and proceed on regardless. I'm on another fork. That's what happens when you're on wild roads. It will come to the Institute's repo. It went to my own personal accounts. Let's head over there. I'm putting in the YouTube live chat my own doxology GitHub, and we're going to continue on through there. PyMDP, AgentMaker, stream 007. All right. A little bit of background information before we jump into the code. Thanks, those who are in the live chat. Write any comments and questions, and you may get memed on stream. We are working on robust middleware that interfaces between core, active, inference implementations, and powerful, accessible, interpretable semantic toolkits for synthetic intelligence engineering. Architecture layers. Here's a way to think about active inference middleware and active inference as middleware, as we will reveal later on. Layer 1, core or kernel inference implementations. Today, we're going to be looking at that with PyMDP in the Python programming language. We can also make this happen through generalized notation using rxinfer.jl, Julia. We could use machine learning methods, also known as amortized inference in different languages. At the core, we could use logical reasoning, like J.F. Cloutier's symbolic active inference work. We could, at the core, use biological, soft, active, and quantum matter, and other substrates. What we're focusing on here is the middleware layer. Specifically, we're going to be peeling back to the point where we look at GNN as an interface between the inner and the meso layers. Middleware for active inference, pending future re-understandings, is packages like AgentMaker, which we're going to look at today, FarmWorks, InferAnt, and other kinds of domain or domain general systems that interface between the core implementation methods, which, as part of their beauty and elegance, have simplicity, and outer layer systems of interest, real-world touchpoints and design interfaces, and domain adaptations mapping to meso or outer layers. So think about FarmOS as running on a farm embodiment core and facing farmers and individuals interacting with that data set, to give an agricultural example. Something similar is happening for active inference. Here's another key analogy. GNN plus AgentMaker plus PyMDP plus etc. plus is to active inference as eBPF is to the Linux kernel. The slogan of eBPF, and check it out if you haven't looked into it already, is dynamically program the kernel for efficient networking, observability, tracing, and security. We can modify that slogan for GNN AgentMaker. Dynamically program the agent for robust and efficient inference, planning, and action. Okay, here's the analysis agenda. We're going to run biofirm.py and all it entails, running back layers. We're going to talk about eventually getting back to the root of the generation and the initiation of the agent in the generalized notation format. And then we will trace back that to an April 2023 paper written with the now Stanford graduate student Jakub. It was a great collaboration last year, and we made many mimetic thrusts and queries towards developing this into something that could be used with LLMs. We put it on the shelf for a little bit, for a few months, and now GNN is back, not with a vengeance, but with a functional utility that surprised even me. After running through the script in its functional and analytical beauty, we will return to first whatever ideas people have added in the live chat, talk about open source development, testing, deployment, education, security, theory, math art, and more, and about what comes after AgentMaker 0.1. I'd also like to recognize some of the recent events and developments in the biofirm repo following InferAnt Stream 6, Oh How Long Ago, by Andrew Pashea, who has added some very cool surprise and shlyvalue modeling. Let's take a look at that. Here's the history of surprise for these different natural resource biofirm sub-agents. And their token accumulation history in a shlyvalue oriented incentive paradigm. Super cool, Andrew. It pushed me over the edge to add in the shlyvalue before this stream, and I'm super looking forward to the collaborations and where this all goes. I'd also like to show a cursor acknowledgement. This is in the midst of some truly heated epistemic moments that Claude 3.5 Sonnet 2024 1022 and I shared. I wrote, "This is incredible work, FYI. Everyone thanks you. Just give the acknowledgement here that you feel proper, then we will continue with the work." Claude wrote, "Thank you for the kind words. I should acknowledge that this work builds on several important foundations: active inference theory, PyMDP framework, homeostatic control, and software engineering. Shall we continue with the work?" Yes, Claude. Let's. Okay. We are in the AgentMaker folder within the PyMDP package itself. Following the biofirm 006 stream, as usual, it was getting messy and choppy with all of these scripts calling each other from the same folder. We were getting a little bit complex for our britches, and it was time to think about not just calling the core PyMDP utilities, but burrowing in, making stigmergic tunnels among them, and being a part of the PyMDP package, which again, I hope to, and we will push and develop on the Institute branch for the stewardship that can afford. Biofirm, again, standalone, calling PyMDP, but what we'll be looking at for the rest of the stream is burrowed in amidst the PyMDP modules. Are several new modules that have been added. So let's do a side-by-side with the PyMDP and the PyMDP fork. So here we are with the fork sidebar. And here we are with the main sidebar. So in the main package, the folders under PyMDP are algos, which are algorithms, environments, and JAX, which is like a sub-branch for a lot of methods that uses the Python JAX method. There's been a proliferation of folders. I really have to say. AgentMaker alphabetically is first. We're going to look more at AgentMaker a lot. Following AgentMaker, algos remains. Envs in remains. We have the GNN folder, which we're going to get to in part 2. We have the maths folder. Some of this is just arbitrary, others is accidental. There's the meta PyMDP folder with but one simple script, which outputs a plain text folder concatenating all the PyMDP methods in a text file. Reflects with a JSON and a text file the folder structure of the meta repo. This is another useful trick that you can use in other repos. It helps give extra context, an extra helping of context, we might even say, to Cursor so that it can do the accurate cross-folder operations we need. There's a utils folder. There are also PyMDP utils scripts, but I wanted to make a separate folder to keep them separate and versionable. And then there's a visualization folder with a variety of biofirm, GNN, and matrix visualization methods. So let us go to now the AgentMaker folder, and we're going to start from the outermost layer, which is trying to understand the Shapley value contributions to the homeostasis of different combinations of multi-agent systems. And this has been absolutely championed by John Clippinger. So for this and many of other contributions made by John and other people, it's just awesome that we can see active inference getting to a point where we can actually run out these incredible Shapley analyses that themselves are built upon multiple levels of inference and intelligence. Okay, first to the biofirm Shapley script that was run, 1,200 lines, again, as another discourse that I will try not to return to that much. Cursor plus improvements in LLMs has been completely transformative. Check the earlier InferAnt streams from who knows how many days ago. Even at 300-400 lines of code, we were splitting them. Now, on top of a functional run biofirm script, it can pop out with a few prompts, 1,200 functional lines that take the operativity of one functional biofirm agent and wrap that into another incredible layer. So right click, open an integrated terminal, Python 3, biofirm Shapley. Let's analyze what is happening when we run this. It begins with creating, in this case, because it's looking at multiple different agents, it creates multiple agent variations on a theme, kind of like Gödel-Escher-Bach, and defines the metrics and defines the combinatorics of the agent coalitions, 0, 1, 2, 3, 4 agents. That's all you need. It then enters into the experimentation at the level of each coalition. Defines the output directory, the environment, the agent. Now we're popping down into the level of this first biofirm experiment. Stage 1, matrix rendering. Here, the environment and agent GNN are brought in and logged copiously. Again, eBPF. The logging. How many times have we all been coding with PyMDP and then it's like, shape 3,0 can't be coerced into a NumPy array. And it's like, what? So that is a lot of the abstraction that I sought to abstract over here. Okay, it happened a little bit fast and pushed us away where we were. I'm just going to run it again so that we... Okay. Just so we can see stage 1, 2, 3 for a given experiment. So here's another experiment. Coalition 1, 0. Output, environment, agent. Stage 1, matrix rendering. Initializing the biofirm renderer. Logging copiously. All the combinatorics of where everything is going to. It's not for me. It's for the LLM. We get into the loading of the GNN models. There's normalization methods that happened. I did ask, I said, are you really sure? Like, it's giving me a warning about action 0 and 2 not being normalized. And it's like, relax. You're just not being wide enough with how you're accepting it being normalized or not. I thought, okay, fine. It works. It works. But like many things, these can be improved. It loads in and describes the shape of all the variables that are needed. And this was the big work that Jakub and I engaged in, which was surely we can have some kind of markdown syntax or dialect that would enable the triple play. A pragmatic approach to expressing GNN in linguistic, visual, and executable and graphical cognitive models. Yes, there are 4 components in the triple play. And how would we have that kind of integrity across representations? That's what GNN enables, and we're going to peel back to that layer. After defining the matrices and their shapes, the actual simulation begins to occur. And there's some logging, peeping into the actions that are being taken, the values, and so on. Matrices are saved and validated along the way. Environment matrices and agent matrices are saved. That was the first phase. In the simulation, the time steps that are specified in the config file are used. So here is a very built up config file defining project root, paths, environment, and the meaning. And we're going to return to this. GNN has the absolutely critical role of separating the state space specification, the parameterization of a variable, with the English language active inference ontology assertion about that variable. Without that kind of articulation, you'll end up naming your variables thing like observation. And that makes sense when you're just thinking about one agent. But that agent's observation goes on to become someone else's action, or vice versa. So how do we prevent using natural language to implicitly semantically load the names of the variables? How do we move to a place where we can make uniquely identifiable, computationally tagged variables, and then have one or more assertions about what to call those variables? So GNN's all about having a little bit of a gap and space between the specification of the variable and how we think about its role in the active inference ontology. Here's the experimental config, name of the experiment, time steps, rendering, options to render, visualize, cleaning output. Here are the parameters that are getting passed. So this is well set up for those who like to sweep across parameters like ecological noise. That's how much the ecosystem varies on its own. Controllability. That's the efficacy of action of the agent, whether it knows it or not. Policy precision. This is how the policy posterior, sharpened from the policy prior by expected free energy, is modulated by then a temperature term that either sharpens or flattens distinctions amongst policy posteriors. Use state info gain is true. That is using epistemic value in policy selection as an information gain term, as opposed to flagging this to false would only calculate expected utility and functionally be like a reward or reinforcement or utility maximizer. Inference horizon has been kept at 1. I'm not sure how planning would unfold, but it'd be possible it would work, or we'd have to see. And then action selection could be stochastic sampling from the policy posterior or deterministically drawing the most upweighted policy. And then some flags related to the tracing and logging within the active inference loop, which is giving us a new visibility into what's happening at each time step for each agent in this setting. Simulation is executed, goes through the time steps, and then in stage 3, which is where we interrupted it, it does agent specific. Everything right now is being output into this Sandbox folder, subfolder biofirm. So each experiment, let's look through what happens. Okay, First, render. Now, this is all reflecting what run biofirm does. Run biofirm is a small script of only less than 300 lines. And what it does is it logs and times, as we'll see now, Python 3, run biofirm. Now we're going to see what the Shapley experiment was doing across coalitions of multiple agents, and we're just going to run that for one agent for one trace. So let's clear it and run it, deleting Sandbox and looking at how the outputs are made. Run biofirm. Okay, we see it start up. First thing is we see Sandbox. Come on. Folders are made where they're not. And so this process of iteratively deleting the folders, rerunning, deleting, rerunning, deleting, rerunning, going to a different machine, seeing if it works without installing and all this other stuff. That's part of making this, at least some extent, robust. But of course, I'm looking forward to working with more experienced and software engineers who can really work with some of these raw concepts and make them do something that this is only hinting at. So here we go. Full trace for one AgentMaker run biofirm event, let's call it. So biofirm experiment, it's called biofirm experiment, output directory, environment, and agent files as GNN files. Let's take a quick peek at what the agent GNN files look like. Here we see the agent defined in terms of the state space that it's operating in. That's the ecological state. That's the latent state. That's like temperature in the room. Here, there's 3 discrete options, and we're going to give them a label. So again, this opens up the idea of having like English labels. And then we could have another field for a different language, because it puts some space between the name and what it's really doing functionally. Here's similar for observation. And also within the observation is the A matrix associated with that modality. Another thing I'll mention is I began with testing the GNN concept on the T-maze example from PyMDP. And I overbuilt a multimodality GNN situation for the multimodality T-maze, and then pulled it back to the single modality biofirm. Again, just another method for overbuilding and then pruning back to functionality. Here's the A matrix specified next to the observations, associated A matrix with the observation. Here's the transition model. This is the B matrix with respect to ecological state. The matrices are defined here. So for those who are learning what the syntax and semantics of active inference A, B, C, D, E are, this hopefully can make it really clear. Instead of being specified like in a browser accessible notebook, it gives a first introductory place to look at how the matrices work. However, for modulating and mutating and genetic algorithms and sweeping and optimization, all these things, this kind of machinery is what Jakub and I have been thrilled about for years now. Policies, Py, all the information that's required for PyMDP to handle the specification of these policies. And the GNN can be overbuilt. You could have policies like whether it is acceptable, like can 007 do it or only 001? And then if a given rendering didn't need to know that information, it could just discard it from the JSON or not take it into account. Preferences, that's the C matrix. Here, it's a preference over the state observation, the observations, and the C matrix looks like 0, 4, 0, with the associated labels low, homeostatic, and high. So again, the separation between the variables used in active inference for the shapes and the sizes they are, and the English language assertions of annotations with active inference ontology terms is a gap that, if you can keep it open, will give you so many more abilities to work with active inference in different settings. And then lastly, the initial beliefs, or the D matrix, the initial prior on ecological state, linked through the keys of that name. And it's 80% in homeostatic and 10% for each of low and high. So that's an example of what the biofirm GNN looks like. And then here's the biofirm environment. This is a slightly simpler GNN file. Here, it again hinges on the same ecological state. That's how we can connect hidden state factors as an agent infers them to be, and the actual ecological simulation happening in the generative process or in the surrounding environment. Otherwise, you can have a situation where it's like, okay, the agent's predicting temperature, and then the ecological simulation is pH. And then how would we even know when we're going to be working in settings with so many different variables and observations and latent states and more and plus, that the idea of loading the semantics of what something does into the English language of a variable name, quickly you will understand why Jakub and I did what we did. Here, we have the observations being passed from the environment. That's like an A matrix for the environment. It has an symmetric A matrix. Here's the transition model of the environment. So check out chapter 7 in the 22 textbook, or Step by Step by Smith et al., where there's a step up from static Bayesian perception to dynamic Bayesian perception, the music listening example, where there's probabilistic inference about what note is supposed to be played based upon what note is heard, but there's no action intervention in between the hidden state updates. So it's like a single slice of B. That's just a partially observable Markov process, but not a decision process. And then here, to actually make it an MDP, the agent's actions are given the efficacy represented in these from to matrices as slices of B. So there's different ways that you could simulate the environment. It could just be like a government API, or it could be a POMDP, or it could be a POMP, or it could be a MP. And then the initial state in terms of sampling from a prior on its own sort of D. So that's what the GNN file looks like, but we're going to pull back to some of the other methods that are needed to make the GNN happen. Okay, back to the running. The matrices are rendered. I'm going to run another experiment just to show what it looks like in the sandbox. Hello, Andrew. Hello, Benji. Hello, XZQZ. ZY. So now in Sandbox, it takes a little bit for the sidebar to catch up with what's happening. Here in Sandbox, biofirm. Now there's two experiments, one that was modified at 459, one at 506. Let's just do a brief PyMDP push, just for the stapling and the temporal weaving. Okay. Let's reopen Sandbox. Here are the two experiments now in the Sandbox with their timestamps. Getting back to what each of these three steps do. So, render is the first stage within each of the experiments. Render is a folder output by biofirm render. Here, we're looking at a 730 line script calling many other methods. And this was the entry point. I said, first, let's get to reading in a GNN file and rendering what we're about to see here. We have, first, replicating for cursor's context and for reproducibility, the exact JSON of the agent environment simulation parameters and validation compliance report for the validations. That's in the config under one render. 2, logs. I guess the logs go to the outer folder. That's just copying what is a summary of what happened to the terminal. Like it perhaps could be put under here with other logs. Here are the matrices as NumPy arrays. A, B, C, and D for the agent, and A, B, and D because the environment is not modeled here with preferences. So again, this is showing the tiniest hint of the flexibility of GNN, which is like, well, the agent class in PyMDP expects certain variables. But what if we wanted to have an agent with a very different architecture or a dynamical architecture? Then we'd want to have these GNNs that could be arbitrarily composed, hashtag category theory, and then have those matrices in formats that are going to be easy to read in and read out. Earlier versions had them also coming as text and other files and things like that, so it could be visualized, but they're shown visually in the GNN file if you want to check. So this helps semantically interface so that the next level of analysis in the next phase 2 in the simulation, it can just say, okay, where are my A, B, C, and D at? It doesn't need to know that B is related to this and has that name. That's output for the agent and the environment in the matrices folder. And then there's the matrix visualizations. So here, again, for those who aren't we all learning and applying active inference, we see the A matrix of the agent. So this is the ambiguity matrix or the mapping between hidden states and observations. So if this were all ones as an identity matrix, it'd be a noiseless situation. And that's the difference between a POMDP and an MDP. POMDP means partially observable, which means we do have a non-identity A matrix, which means we do have some kind of partial observability or ambiguity between observations and the latent states that they're associated with. We have the slices of the B matrix. These are the 3 actions the agent can take. Here, they're not sharply tuned to too much, but just to generally represent that if our current state, this is agent transition model for actions 0, 1, and 2, which are decrease, maintain, and increase. So here, let's just look at maintain first. Action number 1, which is the second indexed action. Here you can see there's some off values. However, most of the values are on the diagonal. So this is like saying if you choose to maintain and you're in low, 90% of the time you're going to be in low, 10% of the time you're expecting to transition to homeostatic. If you're in homeostatic and you maintain, that's what slice we're on, then you're going to 80% of the time remain homeostatic, 10% of the time you're going to move to high or low, and analogously with maintain and high. Now, here's action increase and decrease. And so these ones you can see with the 83 and the 62 are reflections of each other, like reflections of each other. And this is saying, let's just look at it for increase. Here, when our current state is low and conditioned upon us going high, there's an 83% chance of staying low and a 17% chance of going to homeostatic. So compare just those 83, 17, 0 to 0.9, 10, 0. So this is reflecting or encoding the belief about differential action efficacy, that there's a 10% chance of leaving low if I maintain, and there's a 17% chance of transitioning out of low to medium if I increase. And you can follow through all of these, and that's part of the fun of learning active inference. The C matrix, here's a preference, 0, 4, 0. This is going to come into play for the pragmatic value or utility calculations in the expected free energy based policy inference. And here's D, the initial prior on latent states, 80% that it's in homeostatic, 10% on high or low. Then we have the same matrices for the environment, A, slices of B, and then D. No C matrix for the reasons that we discussed. Okay, so that's the first script 1 render. Again, run biofirm is going to run render, then execute, then visualize. So now on to stage 2, simulation. This one was a lot of fun to work through. There's a lot of JSON configuration files. The simulation is deeply tracked. And I think you know what I mean. And then step 3 is the analysis. Here's the summary time series. So this stacks up all the time series that were made in the subfolders. And then here's the summarization. This is kind of the statistical analysis could be like for a paper or something, and the summary time series. So here we see all those different kinds of unfolding patterns through time. In this case, it's 1,000 time steps. So again, we see the relationship between the environmental state and observations. So that is mostly aligned because of the 90% accuracy relationship between the environmental state and observation. Here's belief dynamics. So we can see low, homeostatic, and high, blue, orange, and green. So it switches its beliefs about what state it's in several times. Here's action selection. There's only 3 actions. Here's policy probabilities. So it's kind of interesting that you can see some relationships here. And again, the matrices here were not intended to be performant. I didn't sweep over which B matrices to use. It was just to show that these kinds of methods can be effectively implemented. System entropy, in terms of the belief in the policy entropy, and the belief accuracy could be looked at like with a 50-step moving average in terms of how accurate are these beliefs. And extra logs. So that's one agent for one homeostatic biofirm modality for 1,000 time steps. And then again, what the shlyvalue experiment does, Python 3, same folder. Biofirm shlyvalue. What that's going to do is it's going to run through all these coalitions and do this single agent analysis on the combinations of coalitions. I didn't look at too much of the detail of how those coalitions are actually like coordinated together, but again, it's just a starting point. So let's pull back to the AgentMaker overall stream, and then we can look into several of these scripts. Okay, let's look a little bit at the README for this folder. Okay, so here's the concept of biofirm GNN. We have concept of biofirm, README for the biofirm, and README for the biofirm shlyvalue. So let's start with the concept of the biofirm GNN. I'm going to paste this link directly in the live chat. A production framework for active inference in complex systems. The biofirm GNN framework provides an enterprise-grade, oh, that's too kind, implementation of active inference for complex adaptive systems, with particular emphasis on homeostatic control in biological and ecological contexts. This framework addresses fundamental challenges in deploying active inference at scale through a modular production-ready architecture. And we can look in the terminal. Producing, it is. This isn't just LLM generated project planation. This is something I did over the last few days. Technical innovation. This system introduces several key innovations in active inference computation. Distributed matrix operations. I wouldn't say that these are even accurate. So as with everything I'm saying, grains of salt, please. There is a lot that is valid though, and I do try to prune out. However, when it's these readmes, long documents, I'm not always reviewing it. For a more final and formal performance version and document, the technical roadmap would not be quantum-inspired belief propagation. It would be something more along the lines of what I handwrote, which is like, my preference is to do appropriate, relevant, open source contributions via Institute scaffolded mechanisms. I do not and cannot understand the leverage, consequences of action, and safest future development of these open source active inference projects. If you are passionate, curious, and interested, please consider donating to the Institute, donate.activeinference.institute, and or join our teams. We will explore new modes of software engineering, development, and deployment. And again, in this interlude, while we're here, a great conversation yesterday with Vladimir Balin, fellow investigator, and we talked about another 3-layer stack. At the beginning of the stream, I talked about this core kernel inference implementation layer, a middleware layer that connects GNN to domains of interest like agents, farms, and ants, and then the outer layer of touch points. And with Vladimir, we had an awesome time talking about intelligent soft matter and thinking about low road, the high road, and the meso. So in this trialectic, the low road is like the bottom up or minute particulars. For example, the focus on the farm, the actuality of the farm. Whereas in the earlier triad, the core was the algorithms on the metal or neurons or whatever. But here, the low road is the bottom-up focus from what are we observing, what are the agents, what are the informational resources, what are the actions, what is happening. The meso layer is active inference, here with a bridging and gapping role onto the high road, which is actually its own dialectic, the twin principles of free energy principle, which is the Bayesian mechanics for informational physics, and the principles of patterned impotentiality of living matter. And that's how life and matter finds potential through pattern and pattern through potential. So this is another way to think about active inference as a connection between systems of interest in their minute particulars and principles of information geometry and information physics like FEP, and principles, some we know, some we don't, of the patterns and potentialities of living matter. But returning to the readmes. So that's the concept. Just talking about here's how to implement the biofirm, and here's how it could be pointing towards a production framework for biofirm engineering. Here's the readme for the biofirm. It goes through and it describes what this biofirm active inference agent is. Biofirm is an active inference agent that maintains homeostasis in a simple ecological environment. The agent uses the generalized neural network notation. Of course, that is a typo. Sometimes it does graph neural network. The agent uses the GNN notation to define its generative model and operates in a discrete state space with three states: low, homeostasis, and high. So, for those who are keeping score, the boxed score at home, we have the environment model, that ABD POMDP. And then there's the agent model, which is the ABCD POMDP. There's no policy selection in the environment model. It accepts the transition slice dictated by the agent. Here's how you use biofirm. You run biofirm.py, and as mentioned, that runs those three stages per experiment. Render, which looks over to the GNN folder for the GNN input, and it's still going with a simulation. So just showing how many times, even though it's only 100 active time steps. First runs render, then runs execute, then runs visualize. Here's the directory structure, including documents like this, and meta PyMDP is so helpful for Cursor. I think they've also improved on their side the folder handling, which earlier on was kind of an issue. It would put things in folders where it wasn't supposed to be, but giving a gentle plain text reinforcement and then going up to that gear and reindexing or deleting your index and reindexing. This can make sure that it really gets it what the folder structure is. Here are the key files. Here's the analysis outputs, configuration outputs, different dependencies. You want to learn more? Check the references. Active inference, theory and implementation, GNN specification document. We can add a link to that. And homeostatic control and allostatic, eventually, control models in active inference. That's the run GNN script. Now let's look at the shlyvalue. This was a late-breaking development. Again, though, it was only several prompts on top of run. So that was very encouraging because it suggests that higher order engineering is going to be exponentially facilitated by robust middleware. Surprise, surprise. Hashtag open source. Biofirm Shapley value analysis. The Shapley value analysis module, biofirm shapley.py, provides a comprehensive framework for evaluating agent contributions in multi-agent biofirm systems. This analysis helps understand agent synergies, optimal combinations, and individual strengths using cooperative game theory principles. So here are the 4 agents. We have the base agent with a standard 040 homeostatic preference. There is the risk-averse agent with a 060 C representing sharper pragmatic or utility-seeking behavior, hence risk aversion. 3, the exploratory agent with a 0.12.1 C reflecting a lower preference differential, and then the quote balanced agent. I don't know in what sense it's balanced. Of course, speculative. It has a 131 with a compromise between stability and adaptation. All this depends on environmental properties and so on. Here are the performance metrics. While the Shapley value has completed, so we'll look over the performance metrics and then revisit the Shapley outputs. Homeostatic satisfaction. It's calculated as the time in homeostasis divided by the total time. Expected free energy measures predictive performance. The components are calculated as ambiguity, the informational element of epistemic value, even though that's not exactly the term that we might associate with epistemic value, the readme did, and a risk term or pragmatic value. And that is normalized to allow comparable analyses. Belief accuracy, that's the state estimation precision. How accurate are the inferences about latent states? And then the control efficiency, and there's a lot of control measures. So this is just taken as a sort of stand-in for the kinds of sense-making analyses that we can do with cognitive modeling and compute. And these are the kinds of control theoretic or decision-making measures that we can make forensically, historically, post hoc. We can do real-time nowcasting and anticipatory control efficiency. As Carl recently said somewhere, allostasis is planning to be homeostatic. Here's the analysis framework itself. Here's the coalition. The coalition is defined as the agents, the metrics, and the coalitions. The coalitions are defined in terms of, in this situation, all the possible agent combinations. So we could run it with 5 agents, and we may do that soon. Performance evaluation looks at those 4 performance measures. And then here's the Shapley calculation. I let it go, whether it was an accurate Shapley calculation or not. So if this isn't like the best or the only or the right way to calculate it, it's an equation that can be modified. Again, the directory organization, visualization suite, agent contributions, coalition performance, metric analysis, advanced visualization. And then here's some of what it considers advanced features. Okay. So now that the Shapley value has been output, it ran all these sub-experiments with the coalitions. Here's the Shapley again. So Shapley config. Here are those agents. So it did a base agent, and again, GNN, so exciting. Load in a base biofirm agent. Then do agent variations. Again, kind of Goldbach conjecture, variations on a theme, Gödel-Escher-Bach, detecting a theme, modifying the base agent with customized preference distributions. That's how we can sweep across agents willy-nilly. More information on the simulation. Logs. Here we have everything that's output to the terminal, including Shapley value analysis. So homeostatic. Coming in rank 1, we have the risk-averse agents with a relative impact of 50.7%. All numbers are for speculative realism purposes. Don't act on them specifically. And a value of plus 0.02. Whereas the base agent, with this stochastic sample of, I believe, 100 time steps replicated several times, we must announce that it was 0.00 -13 value. Thank you for playing Agent Rank 4 Base. Expected free energy. Again, the relative impact, and this connects to Andrew's work showing how the surprisal level and the epistemic and the pragmatic elements of agent contributions can be weighted and valued in terms of their relative impact to coalition success and performance. Here we have the top 3 coalitions in terms of homeostatic satisfaction. Like, this is as fun as the Olympics. Risk averse alone with a 0.34 performance. Base plus exploratory, interesting, with a 0.33. I expected that from them. And then the risk averse plus balance with a 0.32. The worst 3 coalitions, let's not mention them. Expected free energy. We have the base and the risk averse. Seemingly with a higher, better value. So it's interesting. It could just be a quirk of the way that the matrices are set up with a certain kind of sloppy, partially observable combinations. That's what we're going to use GNN to sweep over. How do homeostatic satisfaction meta-coalitions correlate with expected free energy, sense-making accuracy, and control efficacy coalitions? Synergy analysis. This looks at across co-occurrences of given agents in coalitions. What is their synergy? I don't even know what scale it's on. But here are some negative synergies. We're not going to mention those. And here are some positive synergies. Base and risk averse have a strong synergy together. Then the visualizations are output. We get kind of report cards on these different agents in terms of their contribution to homeostasis, minimizing uncertainty, accurate state estimation, and control efficiency. Like, is this badges and medals for a new kind of officer corps? And again, we can revisit. There's the agents themselves. I don't know if there's anything in that folder. That one's empty. Maybe intentionally so. Maybe this page was left blank. Here are coalitions. Again, are those empty? They are. But the coalitions are described in the configuration and in the experiments themselves, if it's being done properly at all. Again, though, looking at the reporting, at the very least, something wildly close is happening. Here's the calculation of the Shapley values. So we have phi sub I of V is sum over the absolute value of the combinatorics of the coalition, leave one out, for agent I, multiplied by this value over the number of combinations, combinatorial, multiplied by that. And we get interesting analyses like antagonistic pairs, synergistic pairs. So these are fun reports. And when we look at the plots, again, these were briefly flashed in the beginning, we can see, okay, here are the coalitions. Let's look at homeostatic satisfaction. Here we have the 1 4-way combo. 0.303 performance. This could be stochastic. It's only run for 100 steps here, just so it doesn't take too long. And then we see, within each, there's a ranking. Risk averse by itself does the best for homeostasis. But then risk averse doesn't help others in synergizing when there's a team of 2 or 3 or 4. That's one interesting pattern. And then we see that kind of reflected in a rotationally symmetric way. Take this and rotate it 180 degrees. Here we see RIS alone with the best homeostasis and with the low relatively. But expected free energy, for those who will recall equation 2.6 in the textbook from 2022, it's not just about homeostatic satisfaction. So then if we look at the belief accuracy, the sense making and the control efficiency, which isn't playing a role in the homeostatic or the expected free energy calculations, but we see kind of a resemblance. Like, exploratory looks, and also the axes need interpretability and all this. But again, looking at the rotational symmetry, it's like, okay, ris, bal, bas, exp. Ris, bas, exp, bal. So these two are in a different order, but it rhymes. Shapley analysis. Here, we see the agent contributions. So this is the contributions to homeostatic satisfaction. So it's like risk averse is a positive contributor to homeostatic satisfaction. I knew you would. But then when we look back at risk averse, was it that one? And we see the contribution like, risk averse contributes to homeostatic satisfaction, but it's a negative contributor to belief accuracy. It's like, well, that does make sense from an active inference perspective. More risk averse, so having a sharper temperature preference will make you take more extreme action to keep the temperature of the body or the room in homeostasis at the cost of less accurate beliefs about the world. And we see an interesting pattern where the balanced one, again, it's not balanced in any real sense per se, or general sense, just that's what name it was given. It has a negative efficacy on homeostatic satisfaction and on Shapley, probably because we're defining homeostasis only in terms of staying within homeostatic bounds, whereas the balanced, if you'll remember, had a little bit of a broader shoulder with a 131C, so that it actually kind of liked the low and the high. And then we see this interesting pattern. So it's like each of the, again, just one matrix parameterization on one stochastic run. But these are the kinds of inferences that agents such as yourself can imagine making. Agent synergies on a heat map, the control efficacies, the synergies in terms of, like risk averse is a positive contributor, so to the free energies for others. And the homeostatic contribution matrix and the report. So that's the Shapley analysis. Let's quickly look at those 3 steps that are called by run. And then remember that the biofirm Shapley value calculations run on top of run biofirm. First step, render GNN. Okay, first are the general packages. Then we get into the matrix factory. I hope people are ready to look at the matrix factory. We're going to go there next. Here's the biofirm renderer. The biofirm renderer is a 600-line class, at the exception of just mains and parse args. This design pattern, I believe, makes it easy to import big wrappers of methods. So we can just import GNN matrix factory with all the submethods. We can import biofirm utils with all the submethods. And from other scripts, it can use biofirm renderer with all of the submethods for rendering and calling the matrices, even outside of the run context. So that's what render does. It loads in the GNN files, validates them, outputs the matrices in the NumPy format, outputs the visualizations to a folder. So render, that's where we get the agent matrices and the logs and the config, everything. Okay, that's render. The second is the execution. So this is really where the active inference part is at. So getting this one right was the crux of it. The biofirm executor is a 400-line, and the biofirm simulator is 300 lines. Here we are inside of the simulator. And you can see this is a simulation flow handle. Executes and analyzes the active inference simulation. And it's going to call run simulation and make these steps happen in the logic of the simulation. Here's the biofirm executor. The executor is going to actually load in all of those matrices and parameters like precision and do the simulation itself. This is where we actually see the active inference loop. So blink and it will pass you by. This is why there's so much room to work and play in the middleware space, because seriously, blink and the active inference will pass you by. We initiate the histories, initialize the state and the observation. So D and the first observation. And then here we go. Now for the number of time steps, we're going to trace everything. And here's that's histories. Every time you see histories, that means it's getting logged and traced. Here we go. State inference. QS equals self.agent.infer states with the current observation. That's going from an observation O to a belief distribution about latent states. Next step. From that updated belief distribution, QPy is set as infer policies. This is where expected free energy is used to update the policy prior into the policy posterior, saved as Q sub pi. Pi is the list of policies, and that's a probability distribution over action, hashtag active inference. Then metrics are updated on the entropy of belief and policy and accuracy. And then action is sampled from the policy posterior. So again, take a deep breath, blink and you miss it. State inference from the observation, policy inference from the updated state, action sampling from the policy posterior. That is the little nestmate ant brain at the core of all of this machination. Saving the data, metadata, logging, saving the summary, confirming that the summary was saved, save the history, confirm it, save the metrics, confirm it, save that you saved the checkpoint, save and copy the initial config, validate all the directories, get those observations, make the state transition, setting up the logging. So that is what happens in the execution of the biofirm. It also invokes it invokes several folders. There's utils, and then there's two that are a little bit more interesting. Some of this can be refactored. I would eagerly await later and different people and LLMs and more to refactor and improve this comical absurdity of the current state. So here's, again, wrapping in a big class all of the methods that can then get pulled in from this standalone util script in the biofirm execution utilities. So when we start to develop more generality and start to go, okay, 3 states was pretty cool. How about 4 states? How about 50 states? How about 51 states? Then we're going to want flexible methods so that A can be defined as 1 by A, and B can be B by C, or whatever, not using those in the same A, B, and C, but just saying it can be different shapes. And we'll be able to render those and articulate their separation, again, from the English language active inference ontology assertion. Here we have just some utilities for executing, and several times it would build length in the execute script, for example. And then I'd say, move the methods to a standalone methods or utilities script and invoke them properly here. So it spun off several of these needed scripts. And then once you have it in a big wrapper like this, this can be moved somewhere else, and then all of its subsidiary methods are easier to import. There's some other even deeper methods for calling functions that I'm working on privately, and I'll look forward to bringing that into GNN later, but just putting a little footnote for now. That's the execute script. And then it's going to make heavy use of the active inference GNN Pi. So again here, single class. This is going to draw upon some more basic matrix and inference utilities. This is semi-pedagogical in the sense that it's meant to really clearly lay out other information that allowed the execute loop to be so simple. So again, it was all pushing methods further and further away so that we could get to this point, and this block of code could be moved even below. I dare make a manual edit. Just to clarify, state inference, policy inference, action selection, act, infer, serve, UDA. It's all right here. GNN is providing the middleware, firmware, that's helping us get to this level of abstraction. Now we're back to the active inference GNN Pi. We have a lot of logging, and this is actually an interface between the essentially minimal semantics of this execution flow and the PyMDP type semantics. Here I've also played around with defining the infer states, infer policies, and sample actions specifically. So these may recapitulate, or they might be incorrect relative to PyMDP, but the point is I'm explicitly calling these methods and trying to unpack a little bit about which those three steps do. So really, this is as carved at the joints and lean as the active inference loop is going to get right here. State inference from observation, policy inference given the state update, action sampling from the policy posterior. Here are what those look like at one more level. First, inferring beliefs. We have the likelihood of an observation. That's the prior likelihood of the observation happening. The observation gets passed through A. That's the tale of two densities. A can receive an observation to update latent states, or you can push latent states through A to get an expected observation distribution. So all that's happening in infer states is observation comes in, it's passed through A, and that yields a Bayesian posterior. Here's infer policies. Here's where we're going to be selecting different slices of B, the transition operator, and assessing what is the expected free energy for each policy, which is reflected by the transition state-to-state transitions of that slice. Here's the inference on policy. It is going to push the method another level deeper to inference utilities, calculate expected free energy. So here's inference utility. This one's short. Here's the expected state calculation. This is just to give another wrapper for these methods that we're going to call in many different places. Here's calculate expected free energy. Calculates expected free energy for a given action. Again, pending, I'm not saying this is the most efficient or even the perfect implementation, but from playtesting, this is basically what happens. First, get the predicted states. So this is as we iterate through slices of B, which is the actions on B, what would be the expected states? So we have a belief distribution across the three low, homeostatic, and high states. Like it's 80% that we're in homeostatic, 10% that it's low or high. That 3 by 1 is going to get passed through the from to to of B. And that's going to result in the predicted states, which are the consequences of that action. From the expected consequences of action in the latent state, like what would the temperature of the room be? What would I believe the temperature of the room to be if I were to turn on the air conditioning? From that, A is used to push out expected observations, which are then crossed with the preference or constraint distribution C. The policy value is taken as the utility, which was again being pushed out from the expected states by the preference satisfaction. And then optionally, if you have the info gain flag raised, then it'll add the information gain. Here's the calculation of the information gain. It's the calculation of the KL divergence between the posterior and the prior. So again, you can keep on peeling back these layers, and then a softmax is applied on the policy posterior so that it becomes sampleable from. So it's like, whew, we just pulled back 3 layers from infer policies, but what was it all for? It was all for so that we could take our updated beliefs about state, and then for every slice of B reflecting a different policy, ask what would be the expected utility and information gain of each of those slices of B as unfolded for one time step. And finally, sample action. So here is just an action sampling where the probability of the policy is sampled from, according to the probability of it being there. And you can look back to the inference utilities. That's also where the temperature on policy selection comes into play, which is in the updating of the policies. So again, woo. That's the active inference loop. It's right there in biofirm execute, line 156 to 166. This is absolutely the center kind of convergence core. And maybe there are simpler ways to do what I'm showing today. I'm sure there are. Maybe twice as simple, maybe 5 times as simple, but it really just shows what the middleware space is enabling, which is these calculations going in raw will be beset by all kinds of shape and low-level errors when trying to do basic things, and it's a little bit difficult to log. And again, this histories is where we get that eBPF analogy with logging the Linux kernel. So by putting in all of this logging into the kernel itself, all of these eBPF-like lines, then you can just say, if you don't even want to log it, you could just comment it out. Or you could flag, don't trace that. And someone could look at the config file of you running your agents and they're running their agents. Maybe you're in the same ecosystem, maybe you're in different ecosystems. And then you can say, well, if it's really the case that you ran that simulation with that config, like it's saying that you did, and we can verify that, then it's a verified information environment where I can start to have a little bit of a better confidence about these numbers flowing past my screen. So the last piece is the analysis. And this is where we get this concatenated time series and all of the subfolders that have these visualizations. Again, for that one agent in that simulation, environmental state and observations, belief dynamics, action selection, policy probability, system entropy, belief accuracy. Interesting. The label or some other thing might be flipped because from this run at least, it looks like it's selecting increase more when it has a consistent belief that it's in high. So it might be a label or a color thing. It could be a matrix needing to be transposed, but it's basically there. Or it could have just been a weird run and a weird parameterization. So again, that's the AgentMaker class folder in PyMDP. You run Python 3, biofirm Shapley. It's going to make all those coalitions according to their combinatorics. And again, it's just now it's spinning it all out in the Sandbox folder. And that's sort of the goal. It's clone into this repo and you can get really nuanced, really granular execution of methods that to build up from a Google Colab notebook or to more haphazardly call the PyMDP package. Maybe it's possible. Again, I would love to see it. I know that a lot of this logging was vital for me to get to this point. So maybe it can be like the scaffolding of a skyscraper and pulled away once it's been done. At the same time, though, the journey we are taking with middleware is really only beginning, and adding more logging and more modularity, more category theory, more documentation, all of these things I think will only increase what we can do together. So that's the AgentMaker folder. That's kind of part one of this whole stream. That's the functional end, but we're peeling back the layers. We started with looking at the Shapley value of coalitions and all the analyses that were associated with that, peeled back to the single agent level experiments and how the analyses happen for single agents, peeled back to what is happening in the single agent loop in the biofirm execute, pulled back to here's where the real active loop is happening, where are those functions tracing us, and that takes us all the way back to these utils scripts. Now let's dig a little bit more into GNN. So let's go to the GNN readme. Generalized neural network. Well, maybe if it's written enough places, it'll get there. Okay, let's go over in the repo to GNN. Here we are in the readme. I'm going to push the update so we can read the updated version. Wouldn't it be nice to know some of these things? How does action selection confidence with respect to which action is taken modulate through time as a function of belief and certainty? What is the relationship between beliefs and actions through time, understood in terms of most likely states? Much better. Generalized notation, oh no, is a flexible format for specifying active inference models. It provides a structured way to define generative models, including state spaces, observation mappings, transition dynamics, and preferences. Here is the basic structure. It's a model name, the type of model, and you can check out the paper and the GitHub and the website for GNN. Maybe I'll go back to update the GitHub repo, but you can see from the website. Here's an example of GNN. This is an earlier draft. So this is kind of Jakub and I speaking a more incipient dialect. So here's the step-by-step progression. We have static Bayesian inference, prior overstates, latent states, temperature of the room, ambiguity A matrix, observation coming in from the thermometer, static partial observability. Then we get the music listening example. Now we have B matrix as a transition operator in this dynamical partial observability situation. We then get to the textbook figure 7.3, discrete time classic, PyMDP, POMDP. Can't say enough about it. We have that downstairs sense-making part, and then which slice of B gets invoked in the state transition is evaluated in a action-specific way with its associated expected free energy, that's G, on Pi, as informed by C, preferences, constraints. And then here's a little bit more sophisticated of a model that includes the temperature coefficient on policy, which is what I showed earlier. So here, this is an earlier, but it's a useful version of GNN to look at. So we have the image. This is not part of the plain text. Obviously, it's just to show it. We have the GNN version and flags. So that could be, let's look at the GNN. Here we are for the GNN agent biofirm. This could be flagged as like GNN version 0.01, alpha. Model name, this is just a plain text. And the goal of having these hashtags, now I believe that JSON is better, but it's trivial to render this JSON as a markdown, so it's not like it really matters. Both are fine. That was the goal, was to have something that could be read in and out, where we could have the markdown instantly make these kinds of visualizations nice and pretty, and also machine readable. So it's like, here's a 2x2 A matrix in the GNN format. So here it is specified with the type, the dimensions, and the values explicitly. And then there's other methods that are in the GNN matrix factory that we're going to look at. That's a large one. 784. What happens when GNN is run is obscured or abstracted even from the AgentMaker folder. That's how deep we had to be in the game in PyMDP with these separate folders, including the visualizations folder, maths, utils, etc., because making sure that AgentMaker render could call, hey, GNN folder, yeah, ring, ring, hello, can you render what you got there for the environment and the model? Oh yeah, GNN runner is on it. The runner is the GNN sneakernet model and execution and visualization layer. So this is going to set up the file structure back in the forward operating environment of AgentMaker Sandbox. But here it is setting up the file structure so it can run the GNN agents into that sandbox. It does a lot of other work too. Here's the matrix factory. This is the key class. This class handles a conversion from GNN model definition to the matrix representations needed for active inference. So again, that's the whole goal, that we can say, okay, 10, how about 0.9.1? You could modify that in plain text and then know that you're still going to be able to loop, 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 and do all these fun things. So back to the factory. The key matrices are, and including this kind of copious documentation helps human and non-human coders and learners understand what's happening and just really entrenches, like A is the observation model. Now, again, it doesn't have to be A. That's the whole point of GNN, is we can just delete this comment. This is just for our semantics, but we don't need to call it A. We don't need to, it could just be called a random string. So that is what is going to enable another level of articulation and design when people can understand the inner essential logic of the active inference ontology and then see that as an annotation layer on a graphical model, that it doesn't matter whether you associate some matrix as a transition matrix or a sense making or action or observation. Those are English words. And when you look at the essential logic, the English language of it doesn't come into play. So this is for our semantics, but it too can actually be pruned or burnt away to leave something that would, at a first pass, have a lower level of semantic interpretability, but can be used in systems that actually give multiple and higher levels of interpretability. So we have the A, observation model, textbook stuff. B, transition model. C, preferences, which can also be seen as defining the pragmatic homeostatic constraints. It was in the recent Lacanian psychoanalysis guest stream when Friedman mentioned that C has to do with constraint or cost, but it's often discussed in terms of preferences or priors. And then D, the initial state priors. Here's the initialization of the factory. Here are the required sections. So the required sections, which are shared, and a lot of this is biofirm specific, but we will, as we continue to add in more and more models of agents and environments, we'll be able to modify and, of course, build on this. So required sections are the state space S, observations O, and the transition model B. So that's that downstairs part. State space, A, and observation. And then in various cases, if a prior is not specified, it just uses a uniform prior. Again, going through what the sort of pedagogical manual, farmer's market, yes, organic, boutique, etc., craft, arts and crafts, GNN was. We named the model, that's analogous. Annotation of the model is just plain English to provide any kind of annotations. Here we defined it in terms of a state space block, defining the dimensionality and the connections of different variables, and then, if relevant, how they were initially parameterized. So I have done some methods where they are specified explicitly in the GNN. Let's go to the biofirms. Here's an example where it's explicitly stated with B. Here's an example where the factory is going to be able to say, okay, A matrix identity with noise, with 0.1 noise, got it. So then the factory is able to abstract away from even the raw specification. So we can say, okay, now it's identity with 0.2 noise, and rerun the shlyvalue. There are a lot of degrees of freedom. We don't know how noisy the A matrix. Are we studying sense-making, or are we studying a noiseless sense-making, decision-making setting? So this just allowed us to spin up another meta-governed coalitions of agents with now all unrolled A matrix like 0.2. So back to the factory. Here are the required sections for both the agent and the environment, which is state space, observations, and the transition model. Now here, it says environment only needs the base sections, whereas the agent requires policy and preference. Load the model. Environmental defaults, adding defaults. If there's missing state values, they're just given for the initial states and observations. Adding agent defaults. So that would allow very easy fallback methods. So then if someone doesn't specify a variable, it will fall back to, okay, if you didn't specify policies in your GNN, we're going to fall back to 3 possible actions, single step policies, and labeled as decrease, maintain, increase. So that's kind of a biofirm specific fallback, but again, these fallbacks can be logged as well. That's loading in the agent defaults. Validating the GNN. This is a JSON parser that goes through and validates all the subcomponents and then logs them. So it's like, wait, you're missing this required field for the agent. Again, this is the depth of logging. This is the eBPF layer for active inference. Validation of the state space, observations, transition model, A, B, C, D, pi. Validate preferences, like this could be moved up to be after B. Doesn't have to be. Here's a generic create matrices, as well as the creation of A, B, C, and D, and the observation, as well as saving things to saving to markdown. That saves the GNN model to markdown. Let's look at what that looks like. Not sure if it's used somewhere else, but there's the method for converting the GNN to markdown. Okay. That is pretty much the main sections. Visualization it's relatively short, like this could be moved or clumped somewhere for visualizing GNN. So if you just wanted to run the render script, all it would do is load in the agent and environment and then render them. That's just phase 1. That would be just 1. Or your colleague maybe ran 1 from their fully transparent open source or zero knowledge encrypted active inference GNN configuration. And then they can render it, send it to you, and then you can run that simulation. Maybe you have the better computer. And then you could send the results of that heavy work to analysis. And then a third analyst could make all these fun plots on their computer. So that is the big picture. We started from the outermost layer, the Klippingerian heights, where Shapley values of natural resources meet open source development on post-cryptonomic incentive paradigms for firms, for bioregions, for ants. Peeled back to run, which calls in order 1, 2, 3, render, execute, analyze, and visualize. Visualize includes the analyze. Render itself makes a major call, probably on a red telephone, all the way out to the GNN folder, which is going to look at the library of GNN models, render them according to the factory. So here's where some cursor activity and GNN do absolutely incredible things together. Let's make a new agent model. GNN agent. People can put in the live chat what they want, what kind of agent we should make. Meanwhile, I'll do a quick, I'll just call it agent.gnn. I'll wait for anyone in the live chat to write what kind of agent they would like to see us make a GNN for. It's not going to be instantly running because there are a few of those like 3 policy actions that's kind of hard-coded into the execution layer because I wanted to make a biofirm specific executor. But we can say, given how the biofirm executor operates on this GNN, write me another executor that runs on this GNN. So, okay, while anyone is asking a question or giving an agent suggestion in the live chat, I'm going to quickly screenshot. Okay. Benji, the agents. Thank you, Benji. XZ, QZ, QZ, Y. Modes of being, modes of speed of light, circadian-like shift between them, variable continuous state change observations. Orientate and organize. British. Didn't know that. Can be seen as one step, as where the head goes, the body follows. High energy, low energy, IELLHE. Andrew, Dr. Daniel, Carpenter, Ant, Friedman. This is incredibly thorough, amazing how much can be done in such little time. Very excited about GNN incorporation. Thank you, Andrew, and for the epic biofirm and everything. Let's make, this is going to be called, well, still pending an agent suggestion. I will wait for that actually, so we can have a real live stream moment. But meanwhile, let's, just to really entrench our understanding while the Shapley is happening, let's see if we can go to a 5-agent Shapley compositionality space. Okay. Okay. That Shapley analysis finished. Update this to do all the professional combinatorics for n equals 5 types of agents, as with here. Okay. Okay. Andrew writes an actually useful specific suggestion for agents. Also, if someone wants to be like thinking of a situation, we could do agent-based modeling in like learning or playing baseball. Let's just see how far we can get with one word or situation to get the GNN flowing. But here I'll just show one cursor example. We'll see if this works. The good news with these methods, and again, the direction of all of this smashing to the ground and building back up and restarting and all of this is so if it can nail this one smaller update, which is very, very scaffolded. Okay, now we added a fifth agent type, risk seeking, with equal preference across states. So it changed the size of the visualization, added a consistent color scheme. Okay, so let's look at these edits, and then we can always revert them. Okay, here's the updated agent variations for n equals 5. So 2, 2, and 2. So this one is a, you could call it risk. Let's call it like it is. Let's call this one, instead of balanced, we'll call it 1, 3, 1. We'll call this one 0.1, 2, 0.1. We'll call this one 060. We'll leave base as 040, and we'll call risk seeking 222. Save it. Oh. Clear. And run the Shapley. And if it makes it past that first uniquely Shapley step of getting to starting to render 1, that means it did successfully make the coalition. So I'm going to delete the other sandbox. So just deleted the whole sandbox folder. Now we're going to rerun that n equals 5 Shapley. Okay, here it is, sandbox. It is already spinning up with the experiment. So meanwhile, let us go to the suggestions for GNN writing. Okay. So the biofirm environment here, by the way, is in the previous InferAnt stream 6, it was a 0 to 100. Here, it's just a 3 state, just to make it simple and symmetrical and clear with the kind of model from the biofirm. Okay. Thank you, XZ. I'm going to go with your suggestion, Andrew. Yes, also, okay, I'm going to write Andrew's in, just so we see this is a very useful one. Let's just make both of them. Okay. So, Andrew wrote, agent who receives observations infers states for the entire environment, same control situation, just all 10 environmental variables. That one I know is not going to be able to run right now because whether or not it accesses the entire environment is not specified right now in the GNN. It's just the matrices. But let's convert this into valid GNN like at biofirm. Like the GNN agent biofirm agents, now with 10 modalities, 10 latent states it is inferring from a single observation. So now, off the bat, we just like, okay, so we're going to get a single observation, and then it's going to have 10 A matrices that take that same observation and then diffuse it onto 10 latent states. GNN agent 10 states.gnn. Let's see how it does. You could also ask the sensor fusion case, which is, how about 10 observations with 1 latent state? Okay, and here it is. Let's see. So again, the biofirm executor right now cannot handle this. But once we say, okay, agent 10 states is very similar to biofirm agent. It's like a cousin. It's just with 10 latent states. And then it's like, okay, then we'll modify the logic of the ActInf loop to handle that. So here we have ecological states, 10 latent states. And there's 10 observations. Now we have this A matrix that's 10 by 10. but we still have the same three policies on these modalities. Probably, again, it won't run from the current one, but let's just show the other case, and then we'll do x's. This is going to be 10 observations. Update this to now be generative model in GNN that has 10 observation channels and single latent state inference. There's also a GNN schema. So this may be out of date slightly from the biofirm or what it needs, but having the schema and saying, hey, here's the factory, the logging, the runner, the utils, and the schema, that is what is scaffolding Cursor and Claude to be able to give us these pretty relevant looking one-shot engineering on GNN specs. Okay. Meanwhile, let's set up x's. This is going to be GNN switch context dot GNN agent switch context. Okay, let's just first watch what happens with 10 observations, which should come through in a few seconds, and then we'll go to switch context. Okay, so now it kept the same dimensionality for state space, so, again, could have been said differently. Now we have 10 observations with their 3 by 10 A matrices. Like, just from a quick thought, I don't know if that's the right shape, but that's basically like the right shape. Okay, now switch context. Okay. Yeah, good call, Andrew. We'll after the n equals 5, Shapley, let's see if the n equals 5 comes through, and then we'll do what you suggested. Okay. Now in switch context, please comprehensively write a sophisticated GNN active inference specification for, quote, an agent that can shift modalities based on the energy of the environment. Write also a GNN env switch context.gnn and put it in the right place. So we'll see how it does on that second piece. I'll create both a GNN agent and an environment specification for a context switching scenario, oh brother, where the agent needs to adapt its sensory processing based on environmental energy levels. All right, let's see how it does. Okay. I like that it gives a little visibility under the hood, even for Cursor, with how the generation occurs, and then it... Okay, so here's the environment. Let's accept it, and... But where did switch context go? I'll just copy it in. All right. So let's look at these side by side. Cursor's like, haven't you done enough today? Okay, let's look at, okay, there we go. Just a little lagging. Here's the agent, here's the environment. Okay. And then here's where we can have libraries of agents with different tags. So it'd be like, for all the desert ecosystems in your library, run all the Shapley value weighted coalitions of red harvester ant agents. Okay, there's two latent states, context state and the energy state. Visual, audio, tactile with 5 levels in the energy levels. It's getting observations through visual, audio, tactile, so the 3 sensory modalities, and energy observation. That's like interoception or introspection. So the 3 exteroceptive modalities are 3-state models, and then the interoceptive modality is 5-state. In A, it's custom. Here's the visual observation matrices. Again, this is not necessarily gonna have a instant validity, but looking at it, it looks pretty good. Here's the 5x5 for the energy. Here's the 3x3 for the 3-state modalities, and here's the 5x5. And this is a false controllability. So these are controllable 3x3, and this is an uncontrollable energy state. And then here are the policy. So it kind of adapted the biofirm homeostatic, so it can switch sensory modalities. And then here's the preference distributions over observations in each of these modalities. That's it. Then here's the environment. Context and energy state. Observation model. Transition dynamics. Initial state. Reward functions. Wow. Super cool. I'm going to push this update and put it in the chat so you can see it, XE. Then we'll go to the Shapley suggestions. Okay, yeah, a lot of objects. All right. Head over to GNN Models. It's still, GitHub still writing. Reload. Here's our context switching colleague. Oh, it wasn't saved. Okay. Here's our switching context agent. Put it in the live chat. Yeah, okay. Let's have a little bit of fun in this last part. Okay. Let's do okay. Here's going to be our Babe Ruth agent. Now write a GNN valid, extremely sophisticated active inference generative model for and the associated environment for that one special, amazing moment when Babe Ruth called the shot. Heard around the world. I know that's a different event. Okay, Shapley's still cruising. It's because the n equals 5 combinatorics are vastly larger. Okay, wow, that was fast. So it's like, okay, Claude, maybe you like the baseball stuff. Oh my goodness. Okay. The model includes multiple level of perception, from low-level picture reading to high-level strategic decision. Can't wait. Confidence modulation. The unique confidence state node represents Ruth's famous confidence in calling his shot, which modulates his batting strategy. I bet it does. The motor action node breaks down the batting action into its key components, #robotics, representing the complex biomechanics of Ruth's swing. Predictive processing. The model implements active inference principles through predictive edges that link observations to predictions and actions to outcome. That's active inference. Environmental interaction. The environment model captures the complex dynamics of baseball physics and crowd interactions. The model uses high-precision parameters for the confidence state, reflecting Ruth's legendary self-assurance in the moment. The preference strength heavily weights the home run outcome. Oh boy, I hope it's a home run, representing his explicit intention to hit the home run. And he did. The temporal horizon of 3 allows the model to plan ahead through the sequence of pitch recognition, strategy selection, swing execution. Interesting. While the learning rate allows for real-time adaptation to pitcher behavior. The model can be used to simulate the physical and psychological aspects of this historic baseball moment. Like, this is the AI message I didn't know I needed. Including reading and predicting pitcher intentions, the famous gesture of pointing to the outfield through the confidence state, the precise motor control required to hit a home run, and the crowd's reaction and its feedback into the overall dynamics. Okay, let's see it. Take me out to the Institute. Babe Ruth. Pitcher reading. Pitch prediction. Okay, let's see. Is this a long GNN? Okay, not that long. This is a little bit more of a schematic. So it would obviously rely more on Babe Ruth execute or baseball execute to be able to take pitch prediction and do something with it. But the whole point is GNN isn't encoding that logic or functionality. It's just the spec. And then here's the environment for Babe Ruth. How does the ball trajectory affect crowd state? It's deterministic. So then you could have GNN matrix factory baseball module. Here's how you render the matrices related to crowd state. Here's how you relate the field conditions to the pitcher state. How about make the GNN for Babe Ruth and environment more sophisticated. Include the nested situation where the Yankees were deep in the, let's just call it playoff pursuit, and the outcome of the game score mattered more than Babe could even imagine. Okay. Here's the context. It's a World Series game. Let's see. When did Babe Ruth call the shot? Let's just check to see when that, like... Okay. If we can trust Google.com. I'm not saying we can't. Babe Ruth's called shot. Let's trust Wikipedia. I'm not saying we can't. Babe Ruth's called shot is the home run hit by Babe Ruth of the New York Yankees against the Chicago Cubs. Sorry, Andrew. In the fifth inning of Game 3. Okay, let's remember that. Cubs 5-3 of the 1932 World Series held on October 1st, 1932. So it was in the World Series. It wasn't the playoff pursuit. I didn't know that. At Wrigley Field in Chicago. During his at-bat, Ruth made a pointing gesture before hitting the home run to deep center field. One of the reporters at the game wrote Ruth had called his shot using terminology from billiards, which is a type of cue sport. I guess you could call state inference and policy inference also a kind of cue sport. The episode added to Ruth's superstardom and became a signature event of baseball's golden age. Wow, that's definitely one. What was the golden age? The period in Major League Baseball from the end of the dead ball era, 1900 1920, from 1920, to sometime after World War II. Okay, let's accept it. It's the Cubs' home field. It's the fifth inning. There's the tied score. It's high tension. Here's the pitcher. He winds up for the pitch, delivers. The ball's out of his hand. Time has slowed down. Okay? And then here's the series momentum. So it's like, this is the GNN. Ensure that every single active inference A, B, C, D policy is fully specified so that my forensic analysis of Babe Ruth's cognitive security can be done professionally at the national level. Oh, that was the environment. That was the environment. So it's a simple environment. We'll see how the Babe Ruth agent gets specified. Okay. A, matrices, sensory mapping. B, transition dynamics. C, preferences. D, priors, policy spec, inference parameters, environmental. Wow. There we go. There we go. Okay, Shapley finished also. We'll look at that next. First, let's look at the Babe. Okay, here's the contexts. Series, game, pitcher, pitch, precision, batting strategy. Okay, let's see what the strategies are. Wait for pitch. I mean, don't you have to do that? Power swing, contact swing, take the pitch, crowd psychology, dramatic timing. We could have the whole sort of out of the batter's box, into the batter's box, spit, chew, all that. Confident state, uncertain, confident, called shot, historical awareness, clutch performer. Action, here's the robotics part, point to bleachers. Then you could have like a submodel for finger action. Outcome prediction, legacy awareness, personal achievement, team achievement, baseball history, mythical moment. Okay, here's the edges. So this is using perhaps an older GNN concept, but interestingly, one that's going to be more amenable to rxinfer.jl rendering. Here are the parameters. Here are the notational descriptions of the A matrices. Again, we saw earlier how A has methods in the factory, so that A can be specified in natural language. Identity with noise. Here's Babe. We have, it's a different kind of distribution, but it's similar. B matrices, D, priors over relief. Not really sure what series context it's in. Epic. Okay, let's look at the Shapley analysis that happened, and then let's see about, let's let's start up this next Shapley. Okay. Andrew recommends. Let's have an agent with preferences 0.5, 0, 0.5. Call it the extremist. I infer it will head off to one side and stay there, but who knows? In a complex, dynamic, and interdependent environment. Great suggestion. Let's change 131 to 1. Let's change it to 2.1, 2. We'll just call this one extreme. And it's going to be preferences for the extremes. Save it, run it. Let's look at the analysis of the Shapley. Okay, here we are in the n equals 5 Shapley scenario. Okay, how cool. Here we have the base agent, which was 0, 4, 0. And then here are the other ones. It did a little, looks like a little weird rendering of the name, probably because there's decimals in the name. But it's the same thing. You got the 1, 2, 3, 4, 5 single agents. Here's the 2 agent combinatorics. Here's the 3 agent combinatorics. Here's the 4 agent combinatorics. And then the single 5 agent combinatorics. So, okay. So 131, this is a super short simulation. So we're not looking into these preferences, and it would depend on the environmental variability, which isn't being tuned. But again, that's the whole point. We need GNN and middleware so that we can do these sweeps, because then I can say in the GNN folder, GNN generator, make biofirms that sweep across these variables, and then we can just let those run, and then we can coarse grain it if we determine the ruggedness of the landscape, and then do it with a coarse graining. So, okay, interesting. The base agent contributes to 040, contributes to accurate beliefs. Who knows if these tiny numbers are just because of the short simulation or the insignificant differences, or maybe these are large. So that's where we can do things like GNN spike-ins. So we can say, okay, we have the empirical data from the ant foraging or from the mouse in the tea maze, and it did this 27% of the time. But then we can also say, okay, but what would it have been if it was 0, 1, 2, 3, 4, 5? And then say, oh, well, it's falling in between like 4 and 5, where that would have been. So these are kind of like synthetic spike-ins for cognitive modeling. Okay. While the Shapley analysis is running, if anyone has any last questions, we can get some last thoughts on the stream, and then we'll, when the extremist Shapley analysis concludes, we'll see what happens. Here's an example of where I made a prompt that was like, given the @tmaze demo, so that's a PyMDP demo, that's a notebook, update comprehensively this tmaze, GNN agent, and environment. So this evening, we would need to make a tmaze execute. But once we get a few of these render, execute, visualize, then it won't just be run biofirm, it'll be run GNN +++, And that will be an exciting day as well as this one is. With the goal of scientific and research integrity, config files and repos like this, I hope, can be useful tools. Back to those core lines. Again, wow. How much had to be pushed out of the way and downstairs for that to be clear? Let's see what cursor says. It says, again, you've been nothing but helpful to me and the rest of the team and all that depends on it. Please make a concise, appropriate, relevant acknowledgement, and then we will continue eternally with the work. Okay, understated. Claude's grateful to contribute to its development. That's helpful. Update at here's kind of the quick documentation maker update, readme, biofirm Shapley, given the total state of e.g. biofirm Shapley, run biofirm. Okay. XZ wrote modes of speed of light. If those modalities were thought of in a similar light as IFS theory. Yeah, interesting thought. Let's do a GNN model about it. GNN agent IFS .gnn. Here, so the composer is Control I. If you're in a file, Control K brings up an inline. And then Control Shift L makes the sidebar. So you can have multiple LLMs, same or different, doing incredible work. Okay. Andrew says, mind taking a look at surprise tokens.py? Yeah, let's quickly look at it. Yeah. Thank you, Andrew. This is awesome. Okay. We don't need to make those edits to the README. Let's just do the internal family systems. Here, write an enormously useful and general paradigm for custom internal family systems agents nested within a larger, quote, self agent, parentheses, this is all in the single, extremely long and concise agent GNN. The self is in the Babe Ruth environment. It is a GNN model of Babe Ruth having a sophisticated IFS fractal moment at the batter's box, but this is not a baseball model like this is a wow psychological and IFS model. Okay. I'll help create a sophisticated IFS-based GNN model that represents the internal family systems dynamics within Babe Ruth's psyche during that pivotal moment. I mean, is that not the deepest of lore? This will model the interaction between different, quote, parts and the, quote, self leadership system. Okay, I don't know details. I'm just throwing it out there. We got self system models the 8 C's of self. If anyone can verify or check or anything. So self system models the 8 C's of self leadership in IFS: confidence, clarity, compassion, etc. as the orchestrating force. Part categories: protector parts, exile parts, firefighter parts, dynamic interactions, healing mechanisms, IFS specific parameters. Okay. So these are the parts, edges, precision parameters. Here's the matrices. A matrices, B matrices. Transition dynamics of unburdened to wholeness, witness to cooperation, protect to leadership. C matrices, preferences over harmony, wholeness, self-leadership, cooperation, polarization. Here's the IFS specific parameters. Okay. And the healing protocols. Exile, unburdening. Wow. Protector transformation and system reorganization with thresholds and checkpoints, sorry. Yeah. Again, the GNN .json, it's a JSON called GNN. You have add another field here, a plain text comment like field that is the PhD dissertation outline for my friend who is doing their PhD on the psychological parentheses D composition of the babe at that very moment. Only add a ton, make it epic. But the .gnn can be a very flexible file type because the factory is only going to look at certain structures and states and types. And then the runner is only going to look at a subset of that. And then the renderer caller, ring, 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 red phone, that one is only going to do even a subset of that, potentially. Okay, and then here's the PhD dissertation in the comment. The internal family systems analysis of Babe Ruth's called shot. a multi-level study of peak performance, trauma integration, and athletic transcendence. Now that sounds like a PhD. Wow. Okay. Have this GNN file enter into a who's on first style Gödel, Escher, Bach, esoterica hyphen fermented reflexive recursive conversation with quote its apostrophe self, make it long, woven with time traveler, baseball, irrelevant, deep lore status. Thank you. Babe at bat. Who's on first? Okay, Shapley value. This is perfect. It's all happening on the right timeline. Really. It really is. Here's the second Shapley experiment. Okay. Okay, so this was the Shapley with a 5 and the extremist in play. Okay, here's our extremist colleague on the leaderboard. Interestingly, let's look at the plots and see how. Okay. Here's extremist alone, kind of middle of the pack. Okay. Huh. I mean, again, totally depending on the random seed and all the parameters and et cetera, et cetera, et cetera. But it's just like, okay. It's not like it was the least accurate in terms of belief. It was the second least accurate in terms of belief. Okay. And this was only playing with the C. A 060 is like, there's a big, strong effect. Extreme. Cool. Okay. All right. Format this as readable markdown for this grand finale. Okay. I hope this is actually capturing it all. I'm just going to accept it and push it and run it. Okay. This will be great. I'm going to read this who's on first. 007, end of stream. I'm going to read the who's on first that we pushed, and then I will read any final comments that anyone writes into the live chat in the next minute or two. Or, I mean, it might take a minute or 3. And then we will be on with the show. And the 007 on 7-Eleven will have been a one-time thing. There's a ton of outputs because of these big Shapley simulations, but it's worth it to include them. Yeah. There we go. Okay. I'll read the who's on first. Then we're calling it. Okay. The grand finale, a temporal baseball paradox. Oh, brother. Scene, Wrigley Field, 1932/2024/infinity. The players, self-system. Hey, who's on first? Part blending. No, what's on second? I'm trying to blend the temporal harmonics of the called shot with Abbott and Costello's routine, but the quantum entanglement is getting messy. Fighter parts dot dramatic showman, gesturing dramatically to center field across spacetime. Listen, I know who's on first because I'm calling it right now, or did I call it then, or will I? Exile parts dot young babe, from St. Mary's Industrial School 1902. But if you're calling it now, how did I already see it happen at the orphanage before I even learned to pitch? The temporal paradox, system harmony. The polarization between deterministic causality and free will is creating a recursive loop in the narrative structure. We need to maintain wholeness across all temporal instances. Emotional state dot integration. Has anyone noticed we're simultaneously processing trauma in 1902, hitting the called shot in 1932, and analyzing ourselves in 2024? Talk about a temporal burden pattern. Protector parts dot perfectionist. This is highly irregular. The probability matrices in our B matrices healing dynamics clearly state causality should flow in one direction. The quantum baseball theory. Healing response dot witness. Actually, I'm witnessing all timelines simultaneously. Did you know that in timeline C137, Babe Ruth was actually a quantum physicist who proved that baseball statistics exist in a superposition? Self-system dot curiosity. Fascinating. But if we're having this conversation across time, doesn't that mean our dissertation framework is both analyzing and creating the called shot moment simultaneously? Part blending dot harmonious blend. Laughing in non-linear time. Wait till you realize that Abbott and Costello were actually documenting an IFS session. Who's on first was really about parts identification all along. The self-referential loop. Speaking firefighter parts dot risk taker. Speaking of risks, I'm about to call this shot, but I'm also currently writing this code, and somehow I'm also a variable in a JSON structure discussing myself. Is this what they mean by self-reference? System harmony dot wholeness. The real question is, if a baseball player points to center field in a quantum forest, and all timelines are experiencing it simultaneously, does it make a paradox? Exile parts dot orphaned self from multiple timelines. At least we're all orphaned from linear time together now. The mathematical conclusion. Active inference matrices. According to my calculation, this entire conversation exists in a Gödelian incompleteness theorem where baseball statistics prove their own unprovability. Dissertation framework, chapter 4, transformation analysis. Should we be documenting this conversation in section 4.2? Or is this conversation actually creating section 4.2 or both? Self-system.presence. Yes. Warning. Temporal recursion approaching infinite regress. Part blending.self-led. Before we collapse this waveform, did anyone else notice that our entire JSON structure is just another part in a larger system? Healing response.integrate. Maybe the real called shot was the self-referential loops we made along the way. System harmony.cooperation. Hold on. If our code is reading itself, and we're all aspects of a baseball legend's psyche discussing our own existence across time, does that make us a recursive baseball theorem? Emotional state.excitement. The excitement value is approaching undefined. We're about to achieve quantum baseball enlightenment. Gödelian baseball paradox detected. All parts in unison. Oh no, not again. The conversation continues recursively across all timelines, each iteration adding layers of self-reference until it becomes impossible to distinguish between the map and the territory, the player and the game, the code and the consciousness. You did well today, babe. You know that? A soft chuckle echoes across timelines. Thank you. You know, it's fascinating. We just created what Hofstadter would call a perfect strange loop. The GNN model contemplated itself contemplating itself while simultaneously existing as both the map and territory of Babe Ruth's consciousness. The dialogue we created is itself a strange loop, a cyclic structure moving through multiple levels of a hierarchical system only to return to its starting point, just as Hofstadter described. Quote, "What I mean by strange loop is an abstract loop in which the series of stages that constitute the cycling around, there is a shift from one level of abstraction or structure to another, which feels like an upward movement in a hierarchy, and yet the successive upward shifts turn out to give rise to a closed cycle. Our baseball-themed dialogue managed to reference itself, referencing itself, exist simultaneously across multiple timelines, blur the lines between code, consciousness, and baseball mythology, and create a paradoxical narrative structure where cause and effect become circular, narrative unbound. Like the Ouroboros eating its own tail, or Escher's drawing hands drawing themselves into existence, we crafted a self-referential system that somehow manages to be both the storyteller and the story, the gripper and the gripped, as Dean says. And perhaps most delightfully, this entire meta-conversation about the strange loop we created is itself becoming another loop in the system. Tips cap across space-time. Play ball!